Alrighty, let's get started. So we are starting a new final topic for the semester. This will bring us to the end of the semester. We'll have one more test before the final exam. And this topic is light and optics. So this is a pretty interesting topic. Of course, it's a very large one. Lots of different areas fall under this topic. Very modern physics as well as classical physics deal with these things. And so obviously I can't go through everything. In fact, as you progress through, if you're a physics major, as you progress through the degree, you get to other courses which are purely about optics and modern physics and things like that. So this is more of like an introduction into the topic. But of course, in order to get into it, we need to know about light itself. What is light and the properties of light and things like that. So that's what we'll start with. Light as an entity. What is it? Well, first of all, it is a wave, or at least it can be thought of as a wave. It's not actually a wave. In fact, this is one of the greatest debates in physics, at least it was for hundreds of years, is the nature of light itself. There were those who believed light were particles, like electrons and protons are particles. Well, light is also a particle. And Isaac Newton was one of these people. He believed very strongly that light was composed of different particles. And then the majority of physicists at the time and after Newton, however, thought light was not a particle, but actually was a wave. And the reason is because when they would do experiments with light, the properties that light would show were the same as properties of waves rather than as particles. So during the 1800s, 1800s, and into the beginning of the 1900s, it was pretty much settled that light is a form of a wave until, of course, there were certain experiments that popped up that showed that actually light acts like particles again. And Einstein, in fact, was one of the big people to prove that light had to be a particle, with things like the, different, I'll get into later on. It's not important to get into them now, but there were certain experiments that showed that wave properties could not give the same results as particles could. And so there was a big issue for quite some time that here you have something that we call light that behaves both as a wave in certain circumstances and as a particle in other circumstances. And now, of course, we have basically agreed that both camps are right, that light is both wave-like and particle-like, that the problem, the reason there was such a big issue about it was because we were trying to define light as something else that we know about. We know about waves, like water waves, let's say, and we know about particles like protons and neutrons. And we just expected that light would be one of the two. And it turns out it's neither or both. It's its own type of thing. And in fact, with the advent of quantum mechanics, it turns out that everything in the universe has both wave properties and particle properties. So the issue, what makes this such a confusing and hard to establish thing, is that our minds are limited by our practical experience. and that there must be some other thing out there which is neither a particle nor a wave, but has properties of both. And whatever that thing is, whatever you would call it, that's what light is. Now, of course, we want to get a little bit more specific, not just what kind of properties does it have, but what is it actually made of? And so the best way to discuss it is to first think about it as a wave, and just know that deep down fundamentally, it's not a wave. It has wave properties and it acts like a wave in some circumstances, but it's not just completely a wave. There's another aspect to light that's important as well. So when we discuss waves, we need to know that there's two different types of waves. First, there's transverse waves. And then there's longitudinal waves. And the difference between these two different types of waves is purely how they quote unquote wave. How do they oscillate? So the first, transverse, those types of waves are those that if they move in one direction, let's say the wave is moving from left to right, then whatever the thing is which is waving, the thing going up and down, let's say, always waves perpendicular to the direction of motion. So the waviness is perpendicular to the direction of motion. Okay. And an example of a transverse wave is like a water wave, or maybe a wave on a string. And as an example, let's say you have like a whip. You have a whip and you whip that, you whip it, it looks like this. You got a wave, and that wave travels down to the end of the string or the whip. And then after it reaches the end, it now comes the other way, back this way again. So you have a string, maybe the string is fixed at both ends, and a wave flows through the string from left to right, but the waviness, the thing that's oscillating up and down, is perpendicular to that motion. That is, it's up and down. The string waves up and down, the wave moves left to right. Or if this is a water wave, you're on the beach, you're looking at the Gulf of Mexico, the waves are coming in towards you, so the motion of the waves is towards you, but the wave of the water is up and down. The water wave goes up and then splashes back down again. These are transverse waves. The waviness of it, the oscillation, is perpendicular to the direction of motion of the wave. Longitudinal is the opposite. This is when the waviness is in the same direction as the motion. Okay, so that is to say, if the wave is moving left to right, then the oscillation, the waviness of the wave is also left to right. And an example of this is sound waves. Sound waves, the way they work, let's say here's a person talking, and here's the person they're talking to. There's their ear listening. The way a sound wave works is your vocal cords vibrate, and that vibration causes a pressure difference. You're pushing air out of your mouth towards the person you're speaking to, and it's vibrating at a certain rate. So the pressure wave moving from one person to the next, left to right, let's say, what it does is it takes all the air molecules, so there's a bunch of air molecules all over the place here, just sitting there between you, and the pressure coming from your vocal cords pushes some of the air molecules really close together, and then they relax, and then they push the next set of molecules close together, and then they relax and go back to normal. And so you get this waviness, which is moving in the same direction as the motion of the wave itself. That's what a longitudinal wave is. Transverse, the waviness is opposite or perpendicular to the direction of motion. Longitudinal, the waviness is in the same direction as the direction of motion. Okay. Well, it turns out light is a transverse wave. So the way light works, if you look at its wave characteristics, is it works like a transverse wave. Okay. So there's something about light, which is vibrating or oscillating or waving, and that wave moves in one direction, and whatever the thing is which is waving is perpendicular to that direction. Now, what of course we'd like to find out is what is the thing which is waving, because this is what's unique about light. Every other object or every other type of wave you can think of, the waviness is a waviness of the medium through which the wave propagates. That is to say, if you have a water wave moving through the ocean, well, the wave itself is the water molecules of the ocean being, moved up and down. Or if you have a string and the string is oscillating, let's say it's a guitar string and you pluck the string, and the wave is moving up and down the string through the string as it vibrates. Well, it's the actual molecules of the string. The wave propagates through and it moves the molecules of the string up and down. Or sound waves. As sound propagates, let's say it's propagating through air, then what's being waved, what's being oscillated is the molecules of the air. They're the things that are vibrating back and forth. And of course, sound can travel through other materials. You can send sound through water, and so you can hear things while you're underwater. Or if you're a submarine, you have sonar, you send out a sound wave, it hits the other submarine and reflects back towards you as you listen for it. So sound travels through water as well. And so when it's in the water, it's the water molecules which are being forced by the pressure wave to move, to oscillate back and forth. So every type of wave is waving the material that the wave is going through. However, light is weird, because if we think about light, you say, well, okay, what is waving for light? Well, if we're here on Earth, you could say, well, maybe it's the molecules of the air, right? Light propagates through the air towards us, or you could send light through the water. And so, okay, well, that's fine. Maybe it's like sound in that whatever the medium the light is propagating through, it's moving those molecules around. Except if you think about it, if that were true, then how do we see the light coming from stars? Because stars or the sun, they're out in space where there is no air. There is no medium through which this light can propagate. Yet somehow the light comes to us from a vacuum. So what is it which is oscillating? What's waving? Because if, let's say you have a star explode, you have a supernova. Well, you would think that'd be a loud thing. It would send sound out and you can hear the sound of the explosion of the star. But you can't, because once the sound tries to leave the area of the star and goes into space, well, now there's no more material for the sound to propagate through. So it's silent. You don't hear it, but you can see it. You can see the light coming from it. So although there's no medium for the light to propagate through, it still propagates. So there's still something that's waving. And this was a very big issue when people were trying to figure out how light works. And so one thing that was dreamt up or theorized was something called the ether. And depending on how old you are, it's spelled one of two ways. Physicists for a while said, okay, well, maybe there's this substance in the universe. We can't see it, we can't feel it, but it's just there. It's like space, but it's a substance. And we call it the ether. And it's that substance, whatever that is, that light vibrates up and down as it propagates through. And so, yeah, there's no air, there's no glass, there's no water, but there is this ether. And so that's how the light gets through, which was fine. It's a very good idea. It's a great theory. And so people tried to look for it. People said, okay, if this is true, if there is this ether out there, then we should be able to detect signs of it in some way, other than this indirect notion that, well, it must be there for light to propagate. There must be some direct evidence as well. And so for a long time, ether was something that was just understood, accepted as being the way light propagates. Now, to get to that a little bit more, I have to get into something slightly different, which is one of the physical characteristics. All waves have three basic characteristics associated with them. I'll only discuss one for now, but in a bit, I'll get to the other ones. The first is called the velocity of the wave. So every wave moves at a certain speed. Okay. Sound, for instance, when you speak to somebody else, well, it takes a certain amount of time for those air molecules, the pressure wave pushing the air molecules to get from one person to the other. And in fact, we know the velocity of sound in air is about 343 meters per second. Okay. So every time you're in air and a sound happens, that sound always moves with this speed. Now, if you're in water, because of the way the molecules interact with each other, sound moves at a different speed in the water. It actually moves faster. Or in metal, if you send sound through a metal, the sound moves at an even faster speed through the metal. So different media have different speeds, but when you're in a medium, let's say you're in air, the sound wave always moves with the same speed, and that speed happens to be 343 about. And in water waves, a wave moves through the water at a certain speed. Or a string, you got a wave on a string, it always moves with a certain speed. Now you could do things to change it. You could tighten the string or loosen the string like a guitar, and that'll cause you to have different speeds. But for a set medium, a certain wave will always move at a certain speed. Okay. And it turns out light has a certain speed, the velocity of light, let's say in vacuum or in air. We're going to call it 3 times 10 to the 8th meters per second. Okay. It's not exactly 3. That would be too ridiculous, that it's a nice, perfect round number. It's actually a decimal, but it's close enough to this that we're just going to call it 3 times 10 to the 8th meters per second. And it's so special that we give it its own variable letter. Instead of calling it V for velocity, we call it little c. Okay. So pretty much in physics, if you see the little letter c, it usually means the speed of light. Not always, of course. We've already seen c was also used for specific heat in thermodynamics. But generally speaking, c is set aside as the speed of light because it's a very special number. And so what physicists saw doing experiments is every time they would send off light and receive light from somewhere, it always moved at this speed, which was not all that weird. Like I said, sound always moves at 343 meters per second. So that's fine. And by the way, the fact that these two velocities are different is why if it's, let's say you're New Year's Eve or 4th of July and you're watching fireworks, if the fireworks are kind of far away from you, you'll see the fireworks explode, and then a second or two later, you'll hear it. Well, that's because light travels so much faster that it gets to you before the sound wave could have gotten to you. Because obviously 3 times 10 to the 8th is a very, very, very large number. So that means it moves very quickly. Sound, 300 meters per second, that's very fast, but it's nowhere near the speed of light. All right, well, that's fine. So they found out that light seems to have this special speed. It happens to be 3 times 10 to the eighth, and that's good. Good. So what some people said was, look, if it's true that there's this thing called the ether that permeates the universe, then what I would expect, so let's kind of do a mock drawing. Let's say, here's the sun. Here's the Earth over here. And of course, the Earth is in orbit around the sun. And we're going to assume that there's this ether which permeates all of space. Okay. Well, notice something. As the Earth is orbiting around the sun, the Earth is moving through the space or through the ether in this direction, upwards, let's say, when it's over here. And so if there's this ether all over like this, and light coming from some distant star is coming towards us, and it's vibrating the ether, that's what it's propagating through, then I would expect that when I measure the speed, I would measure it to be a certain number. Okay. Whereas if I'm on this side of the sun, you know, half a year later, 6 months later, now I'm moving back this way, and the same light is coming towards me. Now I'm moving away from the light. So in one time of the year, I'm moving towards the origin of the light, and in the other part of the year, I'm moving away from it. Well, this is important because if you think about what happens in real life, let's say we have a car. There's a car. There's someone on the car, and they're holding a ball. And then here you are over here, looking at the situation. And it's going to be a few different scenarios. The first scenario is this person is standing on a car. The car's not moving or anything, and they throw a baseball towards you with a velocity of the ball is 10 meters per second. And the question is, if you're watching the ball, how fast do you see the ball coming towards you? Well, obviously, you see the ball coming towards you at 10 meters per second. He's just standing there. He throws the ball to you. You see it coming at you. Second situation, the car now is moving towards you with a velocity of 20 meters per second. And you're just sitting there watching the ball. Okay. Well, if the person doesn't throw the ball, you're just watching it, and all you're doing is focusing on the ball itself. You see the ball coming towards you with a speed of 20 because it's on the car. The car is moving at 20 meters per second. So the ball's moving at 20 meters per second. But then the person throws it off the car with his speed of 10. Now what do you see? Well, now you see the ball was already moving at 20, but now someone gave it an extra 10 meters per second of speed. So you would expect that you would have this ball now relative to you moving at 30 meters per second. And then, of course, the last situation, very similarly, you have the car, the ball up here. Now the car is moving away from you with a speed of 5 meters per second. Okay. And then someone throws the ball with a speed of 10 towards you. What do you see? Well, initially the ball was moving away with 5, but now someone gives it an extra 10 towards you. You would see the ball moving at you with a speed of 5. 10 towards you minus 5 away gives you a total speed of 5 towards you. So no matter what happens, what you see depends on the motion of the ball itself, the origin, the actual creator of this thing. If the ball is moving towards you and then someone throws it, its speed must be bigger than it normally would be. If the origin is moving away from you and then they throw it, then it should have a speed lower than it normally would be. That's what you see, and this is true. This is what physics tells us. It's obvious. And so what people thought was, well, this is a way we could test to see if there's the ether. Because if there is the ether, then on one side, on one, at one time, the Earth will be moving towards the origin of light. And so if the light's moving at us with a speed of 3 times 10 to the 8th, and we're moving towards it, let's say our velocity is 1,000, whereas on the other side, it's still moving at us at 3 times 10 to the 8th, but now we're moving away from it with 1,000 meters per second. I would expect that I'd find a slightly different velocity between these two measurements. On one side, it'll be a little bit faster. On the other side, it'll be a little bit slower because I'm moving towards it or I'm moving away from it in these two locations. Okay, any questions about that? Conceptually, does that make sense? Or do you question it? This is what we would expect to see. And this is actually what we see all the time. There's never a time where it's not true. That, if someone is just standing there and they're throwing you a baseball and then you run towards them while they throw you the ball now is coming towards you faster than it was if you were just standing still. Because now your velocity and the baseball's velocity add together or subtract if you're moving away. So they did this experiment. They did it as carefully as they possibly could. And they find out when they measured it on these two, 6 months apart, so we're moving in opposite directions, they find out that the speed of light is exactly the same no matter when you measure it. It never, ever changes. It doesn't matter how fast you as the observer moves, and it doesn't matter how fast the origin of the light moves. Every time you measure the speed of that light, it always is exactly the same number. 3 times 10 to the 8th. Of course, they have the decimal representation, which is way more accurate. But they have never, no physicist has ever done an experiment that measures the speed of light that didn't get exactly the same number if they did the experiment correctly, of course. No matter how you move, no matter how you measure it. So what that means is it can't be that there is this ether, this medium through which light propagates. Because it would have to be that if there is this medium, like if there is, the water and you're swimming through the water, you're moving relative to the water molecules. And if it's the water molecules that are the things that are vibrating, then you would see it at a different speed than if you're not moving. So that's the first big thing is, first of all, there is no ether. Somehow light propagates without a medium. It's the only thing we know of in the universe, which is a wave that does not wave something physical. It doesn't wave molecules. It doesn't vibrate things. Every other wave does. Water waves, string waves, sound waves, everything vibrates something, the thing it's moving through, but light doesn't move through anything. So if this is true, that was a big problem. People had to figure out, well, then what is the thing that's waving? If this is a wave, surely something is moving, something is vibrating up and down. That's what a wave is. Well, it turns out we know exactly what it is. It turns out that what light actually is fundamentally is what's called electromagnetic radiation. That's the formal term for light. Light is just kind of a slang. Electromagnetic radiation is actually what light is. So what is that? Well, electromagnetic obviously is a combination of two different things, electricity and magnetism. And it turns out that when you take the next physics, physics 3, you learn a lot about electricity and magnetism. What you find out is electricity, of course, deals with charged particles. So you have electricity, and all that is how do charged particles interact. So you have positive charges and negative charges. And what you find is when you have a charged particle, let's say we have an electron, and then you have, let's say, a proton over here, they interact with each other. And so if you have two charged particles, they will move or they will apply forces to each other based on their charges. One thing we know is that if they're like charges, they repel each other. And if they're unlike charges, they attract each other. So an electron and a proton will attract each other. But the question is, how do they know? How does an electron know that there's a proton nearby and thus to move towards the proton or to be attracted to it? They don't have eyes. They obviously don't have a brain to think about it. They don't say, hey, look, there's a proton over there. I need to move towards it. They have no, how do they know? And they're not close enough together to actually touch. So it's not like the proton grabs onto the electron in some way. So how does the electron and the proton know to interact with each other? Well, the way we think about it as physicists and scientists in general is that they create what's called a field, an electric field, which propagates out of a charged particle. And this field propagates through space. It's just, if space is completely empty, there's nothing in it, let's say, and you put a proton, that proton creates an electric field throughout all of the universe. And what the electric field does is it tells other charged particles, if you were to put them there, how to move. And so it looks something like this. A proton has these lines coming out, and the lines say how to move. If you were to put another proton, let's say you were to put one right here, well, that proton sees this or feels this line of the electric field and will move along what the line tells it to do. And if you have an electron, the same thing, only moves in the opposite direction. So it'll move towards the proton. And of course, the electron has the same thing. It's got its own lines of field. It creates its own electric field. And then when you have two charged particles, the two electric fields interact with each other and they kind of combine together to make a combination electric field. And in fact, they would connect to each other in this way. I think. And so you will have this electric field, and the electric charges, when placed in the electric field, feel the field and thus know how to move, know how to interact. Okay. And then with magnets, magnetism, you say, well, that's something different. This has to do with poles, magnetic poles. So you'll have like a magnet sitting here with a north pole and a south pole. And kind of similar, you can have two magnets. If you have a south pole near a north pole, then they kind of attract each other. But if you have two north poles, they repel each other. Very similar to electricity. But they look like two different things. One is all about electric charges. The other one is this big solid piece of material, and we call it a magnet, a piece of iron or something. But it turns out that fundamentally, deep down, electricity and magnetism are the same thing, or they come from the same place. Because when you look at what creates a magnet, what makes something magnetic? Think, if you've never thought about it, you should. You have a magnet, it's a piece of iron, let's say. Okay, well, what's iron made of? Iron is made of iron atoms. What's iron atoms made of? Well, it's nuclei, which is just protons and neutrons, and then there's electrons orbiting around. Okay, what's a piece of wood? A piece of wood is made up of carbon and all sorts of different molecules, but what are those molecules made of? Protons, neutrons, and electrons. So it's the same particles. Iron and wood are made of same particles. It's not like one thing has these special magnet particles and these other things don't. Every single thing, every piece of material that you know of is made of the same stuff: protons, neutrons, and electrons, everything. So why is it some things are magnetic and some things are not magnetic, if deep down they're the same particles? Well, the reason is not what they're made of, but how they're put together. What makes something a magnet is the way the electrons themselves move. Okay, electrons, when you get to learn about this, electrons have a spin, and so they have an orientation. If they spin clockwise, they're oriented, we say they're oriented upwards. And if they spin counterclockwise, we say downwards, or vice versa. It doesn't matter. And every electron has a spin, every single electron. No matter what, they all have the same spin, but the spin just may be oriented in different directions. So what makes something magnetic is if in the material, all of the electrons spin in the same direction. And something's not magnetic if all of the electrons in that non-magnetic material spin in random directions. They don't all line up. That's the difference. Magnets, the electrons all line up, so their electrons spin in the same direction. Non-magnets, they don't line up. They spin in different directions. And so deep down, what makes a magnetic property is a charged particle, the electron, but the way the charged particle moves, how it changes. So we get something which is called electromagnetic induction. Electromagnetic induction just means that electricity and magnetism can create each other. If you have charged particles, you have electricity, and you move those charged particles, so let's say you have an electron and you move it through a wire, well, the motion of that electron creates a magnetic field. And so it's like making a magnet. You could put a compass underneath and see it point in a certain direction. And the same goes for magnets. If you have a magnet and you move the magnet around, you could create electricity. If you get a loop or a coil of wire, here's our coil of wire, let's say. Okay, there it is. And you connect it to a little sensor that senses if there's electricity running through the wire. Well, when it's not plugged in, obviously there's no electricity. It's just a wire sitting there doing nothing. But then you stick a magnet into this coil and you move it in and out. You move it through the coil. All of a sudden you get a current running through this wire. Electricity starts to flow. Even though you didn't plug this into the power, it's not plugged into anything, it's just a bare wire sitting there. The fact that there's a moving magnet creates electricity. That's electromagnetic induction. Changing electricity creates magnets. Changing magnets creates electricity. Okay? So what is light? What is electromagnetic radiation? It's nothing more than the electric field, which propagates throughout all the space due to whatever charges there are near it. You have this waviness of the electric field. Here it is. And that waviness is propagating, let's say, left to right. This is the electric field. And it's vibrating up and down. Okay. But remember, electromagnetic induction says if you move an electric field, if you move charges around, you create electric fields. And if those electric fields change because they're moving, that induces magnetic fields. So along with those electric fields vibrating, you also get a magnetic field vibrating. But what's interesting about light is that the direction of motion, first of all, the direction of motion, let's say left to right, and the direction of the vibration of the electric field, up and down, are perpendicular. Remember, that's a transverse wave. The oscillation, the waviness, is perpendicular to the direction of motion. Up and down electric field, left to right is the motion. Well, there's a secondary form which goes with the magnetic field too, is also transverse. So the magnetic field is not just going to be perpendicular to the direction of motion like the electric field is, it's also perpendicular to the electric field itself. So if the electric field is up and down and the motion is left to right, the only other direction left is back to forward. And that's how the magnetic field vibrates, towards you and away from you, towards you and away from you. I'm not very good at drawing this, but I'm trying. And so if you have this wave like this, the magnetic field vibrates towards you and away, towards and away, towards and away. And the electric field vibrates up and down. In that combination of a waving electric field and magnetic field, as it moves left and right, or left to right, that is what is called light. That is electromagnetic radiation. Okay. So that's what light is. Light is a wave, a transverse wave. What is the thing that's waving? Well, what makes light unique is that it's not the material of the medium it's flowing through. It's not the air molecules. It's not the water molecules, but it's the electric and magnetic fields, which are produced by electric charges and magnetic poles. Those electric and magnetic fields oscillate back and forth, perpendicular to each other, always 90 degrees to each other, and always perpendicular to the direction of motion. So it's a transverse wave. Okay, so that's what light is. Now, of course, there's lots of different forms of light. When I say the word light, the first thing that obviously everybody thinks of is when you turn on your lamp or you're looking at the sun or something like that, visible light. But that's not the only form of light. There's lots and lots of forms. There's an infinite, many forms of light. It's just that our eyes, like any camera, are designed in a certain way as to be able to pick up a certain range of light. Our eyes cannot see all of the light in existence, just like when you create a camera cannot see all the light in existence. It can only see what the sensors allow it to see. It's just our eyes are evolved in such a way as to see light of a certain range, which we call the visible spectrum. So we can see red, green, yellow, blue, different colors, which are all forms of light. It's just different colors. But I can't see infrared, or I can't see ultraviolet. Those are different forms of light coming from the sun, but our eyes, the cells in our eyes, just can't detect them. But we know they're there because we can design cameras whose sensors can detect infrared light. And that's what, thermal vision is, when you can see the heat properties using a camera, like the Predator. Or ultraviolet, you can have certain cameras which can get into the ultraviolet range, and so you can see that type of light. But there's, of course, a lot more light than that. There's also radio waves. Most people, when they first hear about radio, of course, everybody thinks of the sound, but radio waves is not sound waves. What you hear are the sound waves produced by a speaker, but the radio itself, what it's picking up, the data it receives to create the sound for you, is actually light. It's just that the light is of a certain, what's called frequency, which is a different characteristic that a radio, an antenna can pick up, and we just can't see that type of light. Or other type microwaves. When you stick your food into a microwave oven, all the microwave oven does is it shoots light at it. Now, the light is not the visible light. It's not the light bulb that lights up when you open the door. It's a different range of light, but that light hits the food. It's vibrating electric and magnetic fields. And so what it does is it vibrates the water molecules in the food, and it vibrates it enough to where that vibration heats up the food due to friction and things like that. So a microwave oven, that just creates light. X-rays, you go to the doctor because you have a broken arm, they take an x-ray of your arm, it's just sending light. It's just that that light is of a certain range that it can penetrate through the skin. Visible light can't. When visible light hits your arm, it's blocked by your arm. It can't get through your arm. But you can create light, which vibrates in a different way, that can get through your arm, but then it's blocked by the bones. And then, of course, you could create light that can get through the bones too, if you wanted to. And of course, there's other light. There's things like gamma rays. Gamma rays are the highest energy, the most dangerous forms of light. The light that you don't want to absorb into your body. So light doesn't just mean the visible spectrum, what we can see. It means all forms of a vibrating or a waving electric and magnetic field. Now, how do we classify these types of light? Like, what makes something visible light and something infrared? How do I know what's different? All it is one of the three big characteristics. Well, let's do it like this. The three physical characteristics. May as well do all three. We already, characteristics, sorry. We've already discussed one, and that is the velocity of the wave. All waves have a certain velocity. Light, of course, its certain velocity is the speed of light, which is 3 × 10⁸. But then there are two more characteristics we need to know about. The first is called F, little f, and it's called frequency. Now the units, let's see, velocity has units, of course, meters per second. It's just the speed of the wave. How fast does it move? It moves in meters per second, obviously. Frequency. The units of frequency, kind of weird. It's 1/seconds. Okay, but that's, yeah, no one likes to say 1/seconds. So people renamed it and called 1/seconds, capital H, little z, which stands for hertz. Okay, so what's the frequency of that wave? 15 hertz or 15 1/seconds or whatever you want to call it, but everybody says hertz. And then the last one is a Greek letter called lambda, and this stands for the wavelength of the wave. And so you can kind of get a clue of what the unit would be. Wavelength means this is measured as a distance, a length, meters. These are the three physical characteristics. Now, we all know what velocity is. That's no big deal. But what the heck is frequency and what is wavelength? Well, let's think about a wave. Remember, this holds for light, but it holds for all waves as well, not just light. So this is more general about waves, not just purely light waves. So what is a wave? Again, it's something, and I'm going to do transverse just because it's easier to draw. A wave is something that oscillates up and down and propagates left to right, let's say. So here's a wave. Okay. Let's say I graph the wave as a function of time. And so I see how the wave oscillates up and down in time. What the frequency is to say, if I graph this in time, and let's say, here's 1 second, here's 2 seconds, 3 seconds, and so forth. The frequency tells you the number of oscillations, or the number of waves per second. Okay, so if we look at our graph, we say, okay, how many waves are there in 1 second? Well, I start here, I've got, that's one full wave. And then here's another full wave. So this particular wave I've drawn has 2 waves per second. So it's 2 hertz. It oscillates up and down twice in 1 second. If you have a wave that vibrates faster, maybe it'd be 10 hertz, 10 waves per second. But that's all the frequency is. The frequency is defined as the number of waves, or the number of oscillations per second. Now there's something else which sometimes is more useful, and that's called capital T, which is called the period of oscillation. And the period is 1 over the frequency. And what does the period say? The period says, how long does it take to make 1 oscillation? How long to make 1 oscillation? Okay, and so obviously this is in seconds, the units. So frequency and period are related to each other. The frequency is, you look in 1 second of time and you count the number of oscillations. The period is, you look at 1 oscillation and you find out how long did that take. So for this particular example, this in one oscillation, which is from here to here, that's only half a second. Because 2 oscillations in 1 second means 1 oscillation took half a second to do. So that's frequency and period. If you know the frequency, you just take the inverse to get the period. If you know the period, you take the inverse and you have the frequency. Very easy. What's wavelength? Wavelength is very, very similar. Let's say we were to, again, draw out a wave. So here's a wave. Only now what I'm drawing is the wave as a function of distance. So this is like you're actually looking at the position. You're looking out at the Gulf of Mexico from the beach, and you see where the waviness is. You say, okay, here's 1 meter, 2 meters, 3 meters, 4 meters, whatever. The wavelength lambda is defined as how far does 1 oscillation go. Okay, so it's the length of 1 oscillation, or 1 wave. Okay, so all you would do, you'd look at the graph and you say, okay, I start here and 1 full wave later, I'm now here. And then you look, how far did the wave travel, or how long is this wave? Well, for this one, it happens to be 1 meter long. So lambda would be 1 meter. The wavelength of this wave is 1 meter long because 1 oscillation is a meter long. That's what wavelength is. It's in the name. The wavelength is the length of 1 wave. And so those are your big characteristics. How fast does the wave move? Basically, how fast is the oscillation? How much does it go up and down in time? And how long is the wave, the wavelength? How are they all 3 related? Turns out they're related by a very easy equation. The speed of a wave is the frequency times the wavelength. Very nice, simple equation to relate to 3. And it makes sense. If you have a frequency of, let's say, 1 hertz, so every second it oscillates 1 time. If the wave moves left to right very quickly, then it's going to, in that 1 second where it waves 1 time, it's going to move a big distance. So it's going to have a long wavelength. But then if you have the same wave moving at, it oscillates 1 time per second, but now it moves very slowly left to right, then it doesn't go very far in that 1 second. So the wavelength is much shorter. So if you have a very high frequency, you have a low wavelength. If you have a very long wavelength, then you have a very short frequency. Okay, it all has to do, given the same velocity. Frequency and wavelength are inversely proportional. And like I said, this holds for light. So if you want it in terms of light, we would say C is frequency times wavelength, where C is the speed of light. If this is a water wave, then V is the speed of water waves. If it's sound waves, then V is the speed of sound. Here, if we're going to be talking about light, then the speed of light is 3 times 10 to the 8th, fancy letter C. So that's light. In a nutshell, that's what it is, theoretically speaking. What is it made of? It's nothing more than the electric and magnetic fields oscillating perpendicular to each other, and that oscillation of fields propagates in some direction. It has certain characteristics. How fast does it move? That's the velocity of the wave. In fact, light, if we're traveling in air or a vacuum, we're going to say it's 3 times 10 to the 8th. If it travels through water, it's a different speed. If it travels through, let's say, glass, it's a different speed. But in air, we're going to call air and vacuum the same. We know it's 3 times 10 to the 8th. Another characteristic is how much does it oscillate? How much does it vibrate? Its frequency. And related to frequency, of course, is wavelength. That is what tells you the color or the type of light we're talking about. If it has a very, very small frequency, so it only vibrates, 1,000 times per second, then it's a radio wave or something like that. If it vibrates very quickly, like 7 billion oscillations per second, then maybe it's light, maybe it's yellow light. And then if it oscillates 15 trillion times per second, maybe it's a gamma ray or ultraviolet. So depending on how quickly it oscillates, depending on its frequency, that'll tell us what type of light we're talking about, or the color. We call color the visible spectrum, but of course we could also call all the different types of light different colors if we wanted to. Now, the reason I don't necessarily say the frequency defines the color, because sometimes people talk about the wavelength defines the color. So if you look up on Google and you say the characteristics of the different colors of light, you'll have a table that says red has a wavelength of blah, 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 blue has a wavelength of blah, blah, blah. Then you'll have other tables that say red has a frequency of something and blue has a frequency of something else. Since frequency and wavelength are related to each other, in other words, if you change the frequency, you automatically also change the wavelength, then we can't really say which one is the thing that defines the color. Because since light always has the same speed, you cannot change the frequency and keep the wavelength the same. That's what this equation says. V being the same number no matter what, if I increase F, lambda has to go down to match. Or if I decrease F, lambda has to go up to match. So one can think, what defines the color of light? You could either call it the frequency that defines the color, or you can think of the wavelength that defines the color. Either way, it's how quickly does it oscillate. That is what defines the color. And that's how we know, are we talking about a radio wave, a microwave, X-ray? visible light, ultraviolet. It all has to do with either the frequency or the wavelength. All right, so any questions about this stuff? All right, well, we've pretty much been going through theory stuff just to understand conceptually what light is. What we're going to do next time is we're going to start getting into some calculations we could run and some of the more analytical stuff we could do about light. For instance, we can create a mathematical equation which defines the certain wave we may be talking about. And with that mathematical equation, we can then input data into it to predict what we would expect, you know, at different times or at different places. So if you, let's say you're at Orange Beach and you're, you know, on the beach looking at the Gulf and you see the waves coming into shore and you watch them long enough where you get enough data, you could fill in the information for the types of water waves you see. You can then take that equation that you create and say, okay, if I wait 4 hours and I look in that part of the Gulf of Mexico, what type of wave or how high will the wave be at that time? Or, you know, how high was the wave 3 minutes ago? You could create a mathematical equation with the information about a wave and then use that equation to predict the future about that wave. And so we're going to talk about that. We're going to see how to develop the equation, what it looks like, and some of the shortcuts people use, because it turns out that sometimes using frequency and wavelength is not ideal because you have to have a whole bunch of 2 pi's in your equations. So people redefine these variables and new variables to make the equation look a lot prettier. And so instead of having frequency, we have what's called angular frequency. Or instead of the wavelength, we talk about the wave number. And it just makes the equation a little easier to see. From there, we're going to talk about things like polarization, which is quite important. You know, the polarization of light is what allows us to do things like 3D movies or create sunglasses that can block out the light from the sun without having to just tint the lens. And then we'll talk about things like lenses and mirrors and things and how to produce images, or if you were to create a lens system, where would you expect the image to be focused, things like this. So that's what we can expect. That's going to be kind of the roadmap till the end of the semester, where we have our final exam, or our last exam before the final. So anyway, next class, we'll get more into this. We'll do some calculations and we'll get some more information. So unless you have any other questions, you are free to go and enjoy the rest of your day. And I will see you on Thursday. All right, you too. Thanks.